IPsec IKEv version 2 overview. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into IPsec IKEv2, which is the second version of the Internet Key Exchange Protocol. IKEv2 is a critical component of modern VPN infrastructure, providing secure tunnel establishment and key management for IPsec communications. Understanding IKEv2 is essential for anyone working with site-to-site VPNs, remote access solutions, or secure cloud connectivity. IPsec stands for Internet Protocol Security, and it's a suite of protocols designed to secure IP communications by authenticating and encrypting each packet in a data stream. While IPsec handles the actual data protection, IKEv2 is responsible for negotiating the security associations and establishing the encrypted tunnels. Think of IPsec as the armor protecting your data, while IKEv2 is the negotiator that determines what kind of armor to use and how to put it on. IKEv2 brings significant improvements over its predecessor IKEv1. It uses fewer messages to establish tunnels, making it more efficient and faster. It has built-in support for mobile users through the MOBIKE protocol extension, allowing seamless transitions between network connections. IKEv2 also includes built-in NAT traversal capabilities, making it work better in real-world scenarios where devices are behind firewalls. Most importantly, IKEv2 is more reliable with features like dead peer detection and automatic reconnection. In this presentation, we'll explore how IKEv2 negotiates security parameters, establishes both control and data channels, and maintains secure communications. We'll look at the exchange patterns, the security associations, and the various authentication methods available. By the end, you'll have a comprehensive understanding of how IKEv2 works under the hood and how to implement it in production environments. IPsec Protocol Architecture. Before we dive into IKEv2 specifically, it's important to understand where it fits within the broader IPsec architecture. IPsec is not a single protocol but rather a framework consisting of multiple components working together. Each component has a specific role, and understanding these relationships is crucial for grasping how IKEv2 operates. The IPsec architecture consists of three main layers. At the top, we have IKEv2, which operates at the control plane. IKEv2's job is to negotiate security parameters, authenticate peers, and establish the security associations that govern how data is protected. Think of IKEv2 as the diplomatic layer that sets up the rules before any actual data transmission occurs. In the middle layer, we have the security protocols themselves. Authentication header, or AH, provides data integrity and authentication but not encryption. It ensures that packets haven't been tampered with and verifies their origin. Encapsulating security payload, or ESP, provides confidentiality through encryption plus integrity and authentication. In modern implementations, ESP is almost always used because encryption is critical for protecting sensitive data. At the bottom, we have the Security Association Database and Security Policy Database. The SAD stores active security associations with their keys and parameters. The SPD defines which traffic should be protected and how. These databases work together to ensure that the right security measures are applied to the right traffic flows. IKEv2 communicates using UDP port 500 for initial exchanges, and UDP port 4500 when NAT traversal is needed. Once IKEv2 establishes the security associations, ESP takes over and protects the actual data traffic using IP protocol 50. Understanding this separation between control plane and data plane is essential because it explains why you will see different port and protocol requirements in firewall rules. Security associations explained. Security associations are the foundation of how IPsec works. A security association, or SA, is essentially a contract between two endpoints that defines exactly how they will protect their communications. Understanding SAs is crucial because they are what IKEv2 spends all its time negotiating and establishing. An SA is unidirectional, meaning you need two SAs for bidirectional communication, one for outbound traffic and one for inbound traffic. Each SA is uniquely identified by three parameters working together. The Security Parameter Index, or SPI, is a 32-bit value that acts as a lookup key. The destination IP address specifies where the protected traffic is going. And the security protocol, either AH or ESP, defines what kind of protection is being applied. Every SA contains specific parameters that govern how data is protected. It includes the encryption algorithm, such as AES-256 or AES-128, which determines how data is encrypted. The authentication algorithm, like SHA-256 or SHA-512, ensures data integrity. The actual cryptographic keys are stored in the SA and used by the encryption and authentication algorithms. The SA also tracks the lifetime of these keys, typically measured in time duration or amount of data transmitted, after which new keys must be negotiated. IPsec uses two types of SAs. IKE-SAs, established by IKEv2, protect the IKEv2 control channel itself. There is only one IKE-SA between two peers, and it is bidirectional. Child SAs, also called IPsec SAs, protect the actual user data traffic. You can have multiple child SAs between the same peers, each protecting different traffic flows or using different security parameters. The lifecycle of an SA is important to understand. SAs are created through negotiation, activated when traffic starts flowing, periodically rekeyed before they expire to maintain continuous protection, and eventually deleted when they are no longer needed or have expired. This lifecycle ensures that keys are regularly refreshed, limiting the impact of any potential key compromise. IKEv2 exchange patterns. IKE version 2 uses a specific pattern of message exchanges to establish secure tunnels. Understanding these patterns is essential because they define the exact sequence of operations that occur when two VPN endpoints connect. The exchange patterns in IKE version 2 are much more streamlined compared to IKE version 1, which is one of the major improvements in this protocol version. The initial exchange is called IKE-SA init, and it consists of just two messages, one request and one response. In this exchange, the peers negotiate cryptographic algorithms for protecting the IKE-SA itself. They exchange nonces, which are random numbers used to prevent replay attacks. They also perform a Diffie-Hellman key exchange to establish a shared secret without transmitting the actual secret over the network. This is mathematically elegant. Both sides end up with the same secret key without ever sending that key across the wire. The second exchange is IKEauth, which also consists of two messages. This is where authentication happens. Peers prove their identities to each other using certificates, pre-shared keys, or EAP methods. The IKEauth exchange also establishes the first child SA, which means you can start protecting user data immediately after authentication succeeds. Configuration parameters, like IP addresses for remote clients, are also exchanged during IKEauth. After the initial setup, IKEv2 uses several other exchange types for ongoing operations. Create child SA exchanges are used to establish additional child SAs for protecting different traffic flows or to rekey existing SAs before they expire. Informational exchanges handle various housekeeping tasks like deleting SAs, reporting errors, or checking if the peer is still alive through dead peer detection. One of the beautiful aspects of IKEv2 is its efficiency. The entire tunnel establishment, from first contact to protected data transmission, requires only 4 messages in the most common case. Compare this to IKEv1, which required 6 messages in main mode or 3 in aggressive mode, but with various limitations. The reduced message count means faster connection times, which is especially important for mobile users or cloud applications where quick connectivity is essential. IKESAINIT exchange details. Let's examine the IKESAINIT exchange in detail because this is where the foundation of the secure tunnel is laid. The initiator, typically called the client or the side that starts the connection, sends the first message. The responder, usually a VPN gateway or server, receives this message and sends back a response. These two messages accomplish several critical tasks simultaneously. In the initiator's message, several important payloads are included. The SA payload proposes one or more transform sets, which are combinations of encryption algorithms, integrity algorithms, Diffie-Hellman groups, and pseudo-random functions. For example, the initiator might propose a ES256CBC for encryption, HMACSHA2256 for integrity, and DH group 14 for key exchange. The KE payload, or key exchange payload, contains the public Diffie-Hellman value calculated by the initiator. The nonce payload contains a random number that prevents replay attacks. The responder's message contains its own set of payloads. The SA payload now contains a single selected transform set, chosen from the proposals the initiator sent. This is the cryptographic suite that will actually be used for protecting the IKESA. The responder includes its own KE payload with its Diffie-Hellman public value. After both sides exchange these values, they can independently calculate the same shared secret. The responder also includes its own unique nonce value. At this point, both peers have enough information to derive keys. They use a key derivation function, typically HMAC-based, to generate multiple keys from the shared Diffie-Hellman secret and the exchanged nonces. These keys include SKD for deriving further keys, SKAI and SKAR for integrity protection in each direction, SKEI and SKER for encryption in each direction, and SKPI and SKPR for authentication payload protection. An important security feature is that IKESAINIT messages are not encrypted because encryption keys don't exist yet. However, they are protected against tampering through the authentication in the next exchange. If an attacker modifies these initial messages, the authentication in IKEUTH will fail, preventing any compromise. This design allows for efficient initial negotiation while maintaining security. IKEAuth exchange and authentication. The IKEauth exchange is where peers prove their identities to each other and establish the first child SA for protecting actual data traffic. This exchange is crucial because it ensures that you are connecting to the legitimate peer and not an imposter. All messages in IKEauth are encrypted and integrity protected using the keys derived from IKESA init. The initiator's IKEauth message contains several critical payloads. The IDI payload identifies the initiator, typically using an IP address, FQDN, or email address format. The auth payload contains the authentication data, which proves the initiator knows the private key corresponding to its identity. This might be a digital signature using RSA or ECDSA, or it could be a keyed hash if using pre-shared keys. The SA payload proposes transform sets for the child SA that will protect user data, separate from the IKE-SA parameters. The traffic selector payloads, TSI and TSR, define what traffic will be protected by this child SA. The initiator specifies which of its traffic should go through the tunnel using TSI, and which responder traffic should be accepted using TSR. These selectors typically include IP address ranges and port ranges. For example, you might specify that all traffic from subnet 10.1.0.0/24 going to subnet 10.2.0.0/24 should be protected. The responder's IKEAUTH message mirrors this structure with its own identity, authentication data, and selected child SA parameters. The responder validates the initiator's authentication, checking digital signatures against certificates or verifying pre-shared key hashes. If authentication fails at this point, the entire exchange is terminated and no tunnel is established. This all-or-nothing approach ensures that partial or weak security states cannot occur. Certificate-based authentication is the most common method in enterprise deployments. The AUTH payload contains a digital signature created using the sender's private key, signing over specific data from the IKESA in its exchange. The receiver verifies this signature using the sender's public key from the certificate. The certificate itself is sent in CERT payloads, and certificate chains can be included to establish trust back to a known certificate authority. Pre-shared key authentication is simpler but requires that both peers already share a secret. The AUTH payload contains a keyed hash created using the pre-shared key and data from previous messages. While easier to configure, pre-shared keys do not scale well because you need a different key for each peer pair, and they do not provide identity protection as robust as certificates do. Child SA establishment. Once authentication succeeds in the IKEAUTH exchange, the first child SA is automatically established. This child SA is what actually protects your user data traffic, so understanding how it is configured is essential for ensuring your applications work correctly through the VPN tunnel. The child SA parameters are negotiated similar to how IKESA parameters were negotiated. The initiator proposes one or more transform sets in the SA payload, and the responder selects one. However, child SA transform sets are typically different from IKESA transform sets. For example, you might use a ES256 GCM for child SAs, which provides both encryption and authentication in a single algorithm, even if the IKESA uses separate encryption and integrity algorithms. The traffic selectors deserve special attention because they determine what traffic actually flows through the tunnel. Each traffic selector specifies an IP protocol, which might be a specific protocol, like TCP, UDP, or ICMP, or the special value 0, meaning all protocols. Port ranges define which application traffic is included, with 0 to 65535, meaning all ports. Address ranges specify the IP addresses covered, and these can be narrow like a single host, or broad like an entire subnet. Traffic selector negotiation can be complex because the initiator proposes what it wants, but the responder might narrow the selectors. For example, if the initiator proposes protecting all traffic from 10.1.0.0/24 to 10.2.0.0/24, but the responder's policy only allows protecting traffic to 10.2.1.0/24, the responder will return narrowed selectors. The initiator must accept these narrowed selectors or reject the entire child SA. After the child SA is established, two more important steps occur. First, the Security Association database on each peer is updated with the new SA parameters, including the negotiated algorithms, the derived keys, and the traffic selectors. Second, the security policy database is updated so that matching traffic gets directed to this SA for protection. From this point forward, any traffic matching the traffic selectors will be automatically encrypted and authenticated using the child SA. Child SAs have lifetimes, typically configured in seconds and bytes. For example, a child SA might be valid for 1 hour or until 100 megabytes of data passes through it, whichever comes first. Before a child SA expires, IKEv2 automatically initiates a create child SA exchange to rekey it, ensuring continuous protection. This rekeying is completely transparent to applications using the tunnel. NAT traversal in IKEv2. Network address translation creates challenges for IPsec because NAT modifies IP addresses and ports in packet headers, which can break IPsec's integrity checks. IKEv2 includes sophisticated NAT traversal capabilities that automatically detect NAT devices and adjust the protocol behavior to work through them. Understanding NAT-T is crucial because most real-world VPN deployments involve NAT somewhere in the path. NAT detection happens during the IKESA init exchange using special notify payloads called NAT detection source IP and NAT detection destination IP. Each peer sends hash values of the IP addresses and ports as seen in the IKESA init messages. When a peer receives these hashes, it compares them with the actual source IP address and port from which the message arrived. If they do not match, NAT is present in the path. Once NAT is detected, IKEv2 switches from UDP port 500 to UDP port 4500 for all subsequent messages. This port change is necessary because port 500 is often problematic with NAT. The use of port 4500 allows NAT devices to properly track and translate the IKE packets. All IKE messages on port 4500 are prepended with a non-ESP marker, which is 4 bytes of zeros, to distinguish them from ESP packets which might also use port 4500. ESP packets themselves need special handling when NAT is present, because ESP does not include port numbers that NAT devices can use for tracking connections. The solution is ESP in UDP encapsulation, where ESP packets are wrapped inside UDP with port 4500 as both source and destination ports. This allows NAT devices to see the UDP header and properly translate addresses, while leaving the ESP payload untouched. NAT keep alive packets are another important aspect of NAT traversal. NAT devices typically have timeout values for their connection tracking tables. If no traffic flows through a NAT mapping for the timeout period, the NAT device removes that mapping. To prevent this, IKEv2 peers send NAT keep alive packets, which are single-byte UDP packets to port 4500, at regular intervals. These packets maintain the NAT mapping even when no actual user data is being transmitted. There are some limitations to be aware of with NAT-T. If there are multiple levels of NAT in the path, things can get complicated. Some NAT devices do not handle ESP and UDP properly, requiring special configuration or firmware updates. Port-restricted NAT can cause issues if port 4500 is blocked, and performance can be slightly impacted by the additional UDP encapsulation overhead, though this is usually negligible compared to the encryption overhead. Dead peer detection and reliability. One of IKEv2's significant improvements over IKEv1 is its built-in reliability features, particularly dead peer detection. In network environments, peers can fail, links can go down, or devices can lose power without properly terminating their VPN connections. Dead peer detection ensures that these failures are detected quickly and handled appropriately. IKEv2 implements DPD through informational exchanges with empty payloads, essentially functioning as heartbeat messages. Either peer can initiate a DPD check at any time by sending an informational request. The receiver must respond with an informational response. If the expected response does not arrive within a timeout period, the peer is considered dead, and the IKESA can be deleted. The timing of DPD checks is configurable and depends on your requirements. Aggressive checking might send DPD requests every 10 seconds, detecting failures quickly but generating more traffic. Conservative checking might use intervals of several minutes, reducing overhead but taking longer to detect failures. Many implementations also use adaptive DPD, where checks become more frequent during idle periods and less frequent when regular traffic is flowing, since regular traffic itself proves the peer is alive. Request retransmission is another reliability feature in IKEv2. If a request message is sent but no response is received within a timeout period, the request is retransmitted. IKEv2 uses exponential backoff for retransmissions, starting with a short timeout like 1 second, then doubling to 2 seconds, 4 seconds, 8 seconds, and so on. After a maximum number of retries, typically 5 or 6, the peer gives up and considers the exchange failed. Message sequence numbers prevent replay attacks and help with reliability. Every IKE message includes a message ID that increments for each new request. Response messages use the same message ID as the request they're responding to. If a request needs to be retransmitted, it uses the same message ID. This allows the receiver to detect retransmissions and can respond with a cached response rather than processing the request again. Cookie-based denial of service protection is another reliability feature. If a responder is under heavy load or suspects a DOS attack, it can respond to IKESAINIT requests with a cookie challenge instead of performing the expensive Diffie-Hellman calculation. The initiator must then repeat its request including the cookie, proving that it received the challenge and is not spoofing its source address. This forces attackers to use real IP addresses and significantly reduces the resources required to handle attack traffic. MOBIKE and mobility support. Modern users are mobile, frequently switching between Wi-Fi networks, cellular connections, or wired Ethernet. Traditional VPN protocols required complete reconnection when the network interface changed, disrupting active sessions. IKEv2's MOBIKE extension, which stands for Mobility and Multihoming Protocol, elegantly solves this problem by allowing seamless network transitions while maintaining the VPN tunnel. MOBIKE capability is negotiated during the IKESA init exchange through a MOBIKE-supported notify payload. If both peers support MOBIKE, it is automatically enabled for that IKESA. The beauty of MOBIKE is that it is completely transparent to upper-layer protocols and applications. Your TCP connections, for example, continue working without interruption even as the underlying IP addresses change. When a mobile device detects a network change, for example, switching from Wi-Fi to cellular, its IP address changes. IKEv2 with MOBIKE handles this through an update SA addresses procedure. The mobile peer sends an informational exchange from its new IP address, including notify payloads that indicate the address change. This message is protected using the existing IKESA keys, proving that it is legitimate and not an attacker trying to hijack the tunnel. The responder validates this update message by checking its authentication and then updates its internal state to associate the IKESA with the new IP address and port. All subsequent IKE messages and ESP packets use the new addresses. Critically, the child SAs and their keys remain completely unchanged during this process. The tunnel data continues to flow with the same encryption and integrity protection, just using different outer IP addresses. Return routability checks add an extra layer of security to MOBIKE. When an address change occurs, the peers might perform a return routability test to ensure that the new address is actually reachable and controlled by the legitimate peer. This prevents certain types of man-in-the-middle attacks where an attacker might try to redirect traffic to themselves by claiming a new address. MOBIKE also supports multi-homing, where a device has multiple network interfaces active simultaneously. The device can test the reachability of different paths and switch to the best one based on performance, cost, or reliability criteria. For example, a smartphone might prefer Wi-Fi when available but automatically failover to cellular when Wi-Fi quality degrades. This intelligent path selection happens without requiring tunnel re-establishment, providing a much better user experience than older VPN protocols could offer. Encryption algorithms in IKEv2. The encryption algorithms used in IKEv2 and IPsec are fundamental to protecting your data confidentiality. Understanding these algorithms helps you make informed decisions about security versus performance trade-offs. Different algorithms offer different balances of security strength, computational efficiency, and compatibility with various devices and compliance requirements. AES, which stands for Advanced Encryption Standard, is the most widely used encryption algorithm in modern IPsec deployments. AES comes in three key sizes: 128-bit, 192-bit, and 256-bit. All three are considered secure by current standards, but they differ in their security margins and performance characteristics. AES-128 provides excellent security with the best performance, making it suitable for high-throughput applications. AES-256 offers the highest security margin, which is often required for government and military applications, though it is slightly slower due to more rounds of encryption. AES can operate in different modes, and the mode selection significantly impacts both security and performance. CBC mode, or cipher block chaining, is the traditional mode where each block is XORed with the previous ciphertext block before encryption. While widely supported, CBC has some limitations, including vulnerability to certain attacks and the inability to parallelize encryption. CTR mode, or counter mode, turns AES into a stream cipher, allowing parallel processing and providing better performance on modern multi-core processors. However, CTR requires a separate integrity algorithm. GCM mode, which stands for Galois/counter mode, is increasingly becoming the preferred choice for IPsec. GCM combines encryption and authentication in a single operation, providing authenticated encryption. This means you get both confidentiality and integrity protection from one algorithm, reducing computational overhead. GCM is highly efficient, especially on processors with AES-NI hardware acceleration, and it supports parallel processing. The combined operation of AES-GCM makes it faster than using separate encryption and authentication algorithms while providing equivalent security. ChaCha20 Poly 1305 is a newer algorithm combination gaining traction, particularly for mobile devices and processors without AES hardware acceleration. ChaCha20 is a stream cipher designed to be fast in software implementations, while Poly 1305 provides authentication. This combination performs excellently on ARM processors commonly found in smartphones and tablets, often outperforming AES on these platforms. Some modern VPN implementations include ChaCha20 Poly 1305 as an alternative to AES-GCM specifically for mobile clients. Integrity and authentication algorithms. While encryption protects confidentiality, integrity, and authentication algorithms ensure that data has not been modified while in transit, and that it comes from the legitimate sender. These functions are critical because an attacker who can modify encrypted data, even without being able to read it, can potentially cause serious security breaches or system malfunctions. HMAC, which stands for Hash-Based Message Authentication Code, is the most common approach for providing integrity and authentication in IPsec. HMAC combines a cryptographic hash function with a secret key to produce an authentication tag. The receiver, who also knows the secret key, can verify this tag to confirm that the message hasn't been altered and that it came from someone who knows the key. The underlying hash function in HMAC determines its security and performance characteristics. SHA-256, which produces a 256-bit hash, is the most common choice in modern deployments. It offers excellent security with reasonable performance. SHA-384 and SHA-512 are variants that produce longer hashes and are required by some security standards, particularly for classified government communications. These longer variants provide higher security margins but are computationally more expensive. SHA-1 is an older hash function that you might still encounter in legacy systems, but it should be avoided in new deployments. Cryptographic weaknesses have been discovered in SHA-1 that make it unsuitable for security-critical applications. If you are working with existing infrastructure that uses SHA-1, planning a migration to SHA-256 or better should be a priority. AEAD algorithms, meaning authenticated encryption with associated data, combine encryption and authentication into a single operation. AES-GCM and ChaCha20 Poly 1305 are both AEAD algorithms. The beauty of AEAD is its efficiency. You perform one cryptographic operation instead of two separate ones for encryption and authentication. This not only improves performance, but also simplifies the protocol because there is one less parameter to negotiate and one less place where implementation errors can occur. When selecting integrity algorithms, you need to consider the truncation of authentication tags. HMAC algorithms typically produce outputs of 256 bits or more, but IPsec allows truncating these to save bandwidth. For example, HMAC SHA-256 might be truncated to 128 bits. While this reduces overhead, you must ensure the truncated length still provides adequate security for your threat model. Generally, 128-bit truncation is considered secure for HMAC algorithms, but some high-security environments may require full-length tags. Diffie-Hellman groups and Perfect Forward Secrecy. Diffie-Hellman key exchange is a mathematical method that allows two parties to establish a shared secret over an insecure channel without ever transmitting the secret itself. Understanding DH groups is essential because they determine the strength of your key exchange and directly impact your vPage's resistance to cryptanalysis. The choice of DH group represents a trade-off between security strength and computational cost. Traditional Diffie-Hellman groups use modular exponentiation over finite fields. Group 2 uses a 1024-bit prime, which was considered secure in the past but is now deprecated due to advances in computing power and cryptanalysis techniques. Some research suggests that nation-state actors may have the capability to break 1024-bit DH in certain scenarios. Group 14 uses a 2048-bit prime and is currently the minimum recommended for most applications, providing security roughly equivalent to a 112-bit symmetric key. Group 15 and Group 16 use 3072-bit and 4096-bit primes respectively, offering higher security margins. Group 15 provides security equivalent to approximately a 128-bit symmetric key, which matches AES 128 and is suitable for most commercial and government applications. Group 16 offers security equivalent to about 150 bits, providing defense against even the most capable adversaries. However, these larger groups require significantly more computational resources, which can impact connection establishment time, especially on lower-powered devices. Elliptic curve Diffie-Hellman groups offer equivalent security to traditional DH but with much smaller key sizes, resulting in better performance. Group 19 uses a 256-bit elliptic curve and provides security equivalent to 3072-bit traditional DH, but with much faster computation. Group 20 uses a 384-bit curve, providing security equivalent to 7680-bit traditional DH. Group 21 uses a 521-bit curve for the highest security level. The performance advantage of ECDH becomes more pronounced on mobile devices and in high-throughput scenarios. Perfect Forward Secrecy is a critical security property that DH groups enable. PFS ensures that if an attacker records your encrypted traffic and later compromises your long-term keys, they still cannot decrypt the recorded sessions. This is achieved by using ephemeral DH key exchanges for each session, so each session has unique keys that are never stored long-term. Enabling PFS for child SAs means performing a new DH exchange when establishing or rekeying each child SA, adding computational cost but significantly improving security. When configuring IKEv2, you specify DH groups for two different purposes. The IKESA uses a DH group specified in the IKESAINIT exchange, and this group's strength should match or exceed your encryption algorithm's security level. Child SAs can optionally use DH groups for PFS, which is specified in the child SA proposal. If PFS is enabled, the same or a different DH group can be used for child SAs compared to the IKESA. Many security policies require PFS for all SAs to ensure maximum protection of sensitive data. Certificate Management and PKI. Public key infrastructure is the foundation for scalable and secure certificate-based authentication in IKEv2 deployments. Understanding PKI is crucial for enterprise VPN implementations because certificates provide strong authentication without the operational burden of managing individual pre-shared keys between every peer pair. A well-designed PKI enables secure authentication while remaining manageable even in large deployments with hundreds or thousands of VPN endpoints. At the heart of PKI is the Certificate Authority, which is a trusted entity that issues digital certificates. The CA signs certificates using its private key, and anyone with the CA's public key can verify these signatures. In IKEv2, each peer has a certificate issued by a CA, and during authentication, peers exchange certificates and verify them against the trusted CA. This creates a trust model where you don't need to individually trust each peer. You only need to trust the CA that issued their certificates. Certificate enrollment is the process of obtaining a certificate for a VPN endpoint. This process typically involves several steps: generating a key pair on the endpoint, creating a certificate signing request that includes the public key and identity information, submitting the CSR to the CA, having the CA verify the identity and sign the certificate, and finally, installing the issued certificate on the endpoint. Automating this process is important, especially in large deployments. Protocols like EST, which stands for Enrollment over Secure Transport, provide standardized methods for automatic certificate enrollment. Certificate validation during IKEv2 authentication involves several checks. The peer verifies the digital signature on the certificate using the CA's public key, ensuring the certificate was actually issued by the trusted CA. It checks the certificate's validity period to ensure it hasn't expired and isn't being used before its not before date. It verifies that the certificate hasn't been revoked by checking certificate revocation lists or using the online certificate status protocol. The peer also validates the certificate chain, following the chain of trust from the peer certificate up to a trusted root CA. Subject alternative names in certificates are particularly important for IKEv2. The SAN field can contain various types of identifiers, including IP addresses, DNS names, email addresses, or other identifiers. During IKEv2 authentication, the identity payload must match ASAN in the certificate. For example, if a peer identifies itself as vpn.example.com, the certificate must have that DNS name in ASAN. This binding between the IKEv2 identity and certificate prevents attackers from using valid certificates for illegitimate purposes. Certificate lifecycle management is an ongoing operational concern. Certificates have limited lifetimes, typically 1 to 3 years, after which they must be renewed. Planning for certificate renewal before expiration is critical because expired certificates will cause VPN connection failures. Many organizations implement automated certificate renewal processes that obtain new certificates 30 to 60 days before expiration. Certificate revocation is needed when a private key is compromised, when an employee leaves, or when a device is decommissioned. Ensuring that revoked certificates are actually checked during authentication is important. Some implementations skip revocation checking for performance reasons, which can create security vulnerabilities. Traffic selector negotiation details. Traffic selectors are a critical but often misunderstood component of IPsec configuration. They define precisely which traffic flows through the encrypted tunnel and which traffic goes directly to the internet. Misconfigured traffic selectors are one of the most common causes of VPN connectivity issues, where the tunnel establishes successfully but applications still can't communicate because their traffic isn't matching the selectors. Each traffic selector is defined by 5 components working together. The IP protocol number specifies which protocol the selector covers. TCP is protocol 6, UDP is protocol 17, ICMP is protocol 1, and the special value 0 means all protocols. The IP address range defines which source or destination addresses are included, using a starting address and ending address. While this is often expressed as a CIDR subnet like 10.1.0.0/24, internally it's stored as a range from 10.1.0.0 to 10.1.0.255. The port range specifies which transport layer ports are included, with 0 to 65535 meaning all ports. Traffic selector narrowing is a powerful but complex feature. The initiator proposes traffic selectors in the IKEv2 or create child SA exchange, typically proposing broad selectors that cover all the traffic it wants to protect. The responder examines these proposals against its local security policy. If the responder's policy is more restrictive, it narrows the traffic selectors to match its policy. For example, if the initiator proposes protecting all traffic from 10.1.0.0/24 to 10.2.0.0/16, but the responder's policy only allows protecting traffic to 10.2.1.0/24, the responder returns narrowed selectors covering only that subnet. The initiator must then decide whether to accept these narrowed selectors or reject the child SA entirely. This creates an important design consideration. Should your VPN fail closed, refusing connections when traffic selectors do not match exactly, or fail open, accepting narrower selectors and only protecting a subset of traffic? The right choice depends on your security requirements and operational needs. In high-security environments, failing closed prevents data from accidentally bypassing VPN protection. In availability-focused environments, accepting narrowed selectors ensures connectivity even with policy mismatches. Multiple child SAs can exist between the same peers with different traffic selectors, allowing you to apply different security policies to different traffic types. For example, you might have one child SA with AES-256 and PFS for protecting database traffic, and another child SA with AES-128 without PFS for protecting general office traffic. This selective application of security policies lets you balance security requirements against performance costs. Each child SA is independent, with its own keys, algorithms, and traffic selectors. Traffic selector conflicts can occur when overlapping or duplicate selectors exist, and resolution depends on the implementation. Most implementations use a most specific match approach, where traffic is matched against the most specific selector covering it. Understanding how your particular VPN implementation handles selector overlap is important for troubleshooting. Some implementations maintain a priority list of child SAs and match traffic against them in order. When troubleshooting traffic selector issues, packet captures showing whether traffic is being encrypted or sent in clear text are invaluable for diagnosing selector mismatches. IKEv2 configuration payloads. Configuration payloads in IKEv2 allow the responder to assign configuration parameters to the initiator during tunnel establishment. This is particularly important for remote access VPNs where mobile clients need to receive IP addresses, DNS servers, and other network configuration from the VPN gateway. Understanding configuration payloads is essential for implementing remote access solutions that work seamlessly with client applications. The most fundamental configuration attribute is the internal IP address assignment. When a remote access client connects to a VPN gateway, it needs an IP address that belongs to the corporate network. The gateway assigns this address through an internal IP4 address or internal IP6 address attribute in the IKEv2 exchange. This address becomes the inner IP address used for the encrypted tunnel, while the client's real IP address remains the outer address on the tunnel packets. Applications on the client use the internal address, making them appear as if they are physically present on the corporate network. DNS configuration is critical for seamless user experience. The internal IP4 DNS and internal IP6 DNS attributes provide DNS server addresses to the client. These DNS servers typically belong to the corporate network and can resolve internal host names that external DNS servers wouldn't know about. Many organizations use split DNS, where internal domains are resolved by corporate DNS servers and external domains by public DNS servers. Some clients support this through split horizon DNS configuration received via IKEv2. The internal IP4 subnet attribute tells the client which destination networks should be sent through the VPN tunnel, or directly to the Internet. This enables split tunneling, where only corporate traffic goes through the VPN, and internet-bound traffic takes the direct path. Split tunneling improves performance and reduces load on the corporate VPN gateway, but it also creates security considerations, because the client simultaneously connects to trusted and untrusted networks. Some security policies mandate full tunneling, where all traffic must go through the corporate gateway for inspection and filtering. Additional configuration attributes provide other network parameters. The internal IP4 mask specifies the subnet mask for the assigned IP address. However, this is less commonly used with modern CIDR-based configurations. The application version allows exchanging information about VPN client and gateway software versions, which can be useful for compatibility checking or security audits. Some vendors define proprietary configuration attributes for features specific to their implementations, such as always-on VPN settings or additional security policies. Configuration request and response flow works in a specific pattern. In the IKEv2 exchange, the initiator includes a CFG request payload listing the configuration attributes it wants to receive. Common attributes include internal IP address, DNS servers, and split tunnel routes. The responder processes this request, allocates resources like IP addresses from a pool, and returns a CFG reply payload containing the assigned attributes. The initiator then applies this configuration to its network stack, configuring virtual interfaces, routing tables, and DNS settings based on the received parameters. This configuration remains active for the lifetime of the IKESA and is removed when the VPN disconnects. Rekeying procedures and key lifetimes. Cryptographic keys should not be used indefinitely because extended use increases the risk of key compromise and reduces security margins. IKEv2 implements sophisticated rekeying procedures that automatically refresh keys before they expire, ensuring continuous protection without service interruption. Understanding rekeying is important for configuring appropriate lifetimes and troubleshooting connectivity issues that can occur during key rollovers. Key lifetimes can be specified in two ways: time-based and traffic-based. Time-based lifetimes specify how long keys can be used, typically measured in seconds. Common values range from 1 hour, 3600 seconds, to 24 hours. Traffic-based lifetimes specify how much data can be encrypted with the keys, measured in kilobytes. For example, you might configure a lifetime of 100 megabytes. Whichever limit is reached first triggers rekeying. The rationale behind traffic-based limits is that encrypting more data with the same key provides more ciphertext for cryptanalysis, potentially weakening security. IKESA rekeying uses the create child SA exchange to establish a new IKESA while the old one is still active. The peers negotiate new cryptographic parameters, perform a new Diffie-Hellman exchange to establish fresh key material, and create the new IKESA. Once the new IKESA is established, new child SAs are created under it, and old child SAs are gradually deleted. Finally, the old IKESA is deleted. This overlapping approach ensures there is no moment when protection is unavailable. Child SA rekeying is similar but simpler because it happens within an existing IKESA before a child SA's lifetime expires. One peer initiates a create child SA exchange proposing parameters for a new child SA if perfect forward secrecy is enabled. This exchange includes a new Diffie-Hellman exchange. Once the new child SA is established, traffic seamlessly transitions to using the new keys. The old child SA is kept briefly to ensure in-flight packets are properly processed, then deleted. During this transition, both SAs temporarily exist, but traffic flows through the new one. Soft and hard lifetimes provide a safety margin for rekeying. The soft lifetime is when rekeying should begin, typically set to 90% of the hard lifetime. When the soft lifetime is reached, the device initiates rekeying. The hard lifetime is when keys absolutely must not be used anymore. If rekeying hasn't completed by the hard lifetime, the SA is deleted, potentially causing a service interruption. The gap between soft and hard lifetimes provides time for rekeying to complete even if there are delays due to network issues or processing load. Simultaneous rekeying occurs when both peers independently decide to rekey at almost the same time, resulting in two overlapping create-child SA exchanges. IKEv2 handles this through collision detection, using message IDs and nonces. When a collision is detected, one exchange is accepted and the other is deleted, with the peer that wins the collision continuing with its rekeying request. This prevents the creation of duplicate SAs and ensures proper state synchronization. This collision handling is automatic and transparent, although it can appear in logs as failed rekeying attempts, followed by successful ones. Troubleshooting IKEv2 connections. Troubleshooting IKEv2 issues requires systematic diagnosis because problems can occur at multiple layers: network connectivity, firewall rules, configuration mismatches, authentication failures, or certificate problems. Developing a methodical troubleshooting approach saves time and helps you quickly identify the root cause. Understanding what information to look for in logs and captures is essential for effective diagnosis. The first step is always verifying basic network connectivity. Can the initiator reach the responder on UDP port 500? Use ping to verify IP reachability. Though note that some security policies block ICMP, use Telnet or Netcat to test UDP port 500 connectivity, or use specialized tools like IKEv2 Scan that speak the IKEv2 protocol. If NAT is involved, verify that UDP port 4500 is also reachable. Many IKEv2 failures are simply due to firewall rules blocking the required ports or security groups not allowing the traffic. IKEv2 debug logging is your primary tool for diagnosing negotiation failures. Most VPN implementations offer multiple debug levels. Basic logging shows major events like SA establishment and deletion. Detailed logging shows all IKEv2 messages, payloads, and cryptographic operations. Packet-level logging shows the actual bytes transmitted. Start with detailed logging to see the message exchange. Look for where the exchange stops. Does it fail after IKESAINIT, suggesting a proposal mismatch? Or does it fail during IKEAUTH, suggesting an authentication problem? Proposal mismatches occur when peers cannot agree on cryptographic parameters. The initiator proposes several transform sets, and if none of them are acceptable to the responder, the negotiation fails. Logs typically show no proposal chosen or no acceptable proposal errors. To fix this, ensure that at least one proposal on the initiator matches what the responder accepts. Common mismatches include using deprecated algorithms like 3DES or SHA-1 that one peer rejects, or requiring stronger algorithms like AES-256 that the other peer does not support. Authentication failures have distinct symptoms. If authentication fails, the IKEauth exchange completes, but returns an authentication failed notification. For certificate-based authentication, check that certificates are valid, not expired, signed by a mutually trusted CA, and contain the correct subject alternative name matching the peer identity. Verify that certificate chains are complete, and that revocation checking isn't failing due to unreachable CRL or OCSP servers. For pre-shared keys, verify that both peers have the same key configured. Even a single character difference will cause authentication to fail. Traffic selector mismatches are a common problem. The tunnel establishes successfully, but applications cannot communicate. This happens when the negotiated traffic selectors do not cover the actual traffic that applications are sending. To diagnose this, compare the configured traffic selectors with the actual source and destination addresses of application traffic. Packet captures showing packets being sent in cleartext instead of being encrypted confirm selector mismatches. The fix usually involves adjusting the traffic selector configuration to properly cover the needed traffic ranges. Packet captures provide the most detailed view of what is happening on the wire. Capture on both initiator and responder if possible to see both perspectives. Filter for UDP port 54500 to isolate IKEv2 traffic. Wireshark can decode IKEv2 packets, showing payloads and their contents. However, after IKESAINIT, packets are encrypted, so you will only see encrypted blobs. Tools like IKEscan can perform active probing to test responder configuration without requiring initiator configuration, which is useful for testing VPN gateways from external networks. IKEv2 in cloud environments. Implementing IKEv2 in cloud environments introduces unique considerations compared to traditional on-premises deployments. Cloud platforms have specific networking models, managed services for VPN connectivity, and architectural patterns that influence how you design and deploy IPsec solutions. Understanding these cloud-specific factors helps you build robust and scalable VPN connectivity between on-premises networks and cloud resources or between different cloud regions. Cloud virtual networks have characteristics different from physical networks. In AWS, VPCs provide isolated network environments with software-defined networking controlling routing and security. In Azure, virtual networks offer similar isolation with additional integration into Azure services. In Google Cloud, VPC networks are global by default with regional subnets. These differences impact how you configure traffic selectors and routing for IPsec tunnels. Understanding the cloud provider's networking model is essential for proper configuration. Managed VPN services offered by cloud providers handle much of the IKEv2 complexity for you. AWS VPN uses IKEv2 for its site-to-site VPN connections, automatically managing the responder side configuration. You specify high-level parameters like customer gateway IP, BGPASN for dynamic routing, and pre-shared keys or certificates for authentication. AWS handles the IKEv2 negotiation details, rekeying, and dead peer detection. Azure VPN Gateway similarly provides managed IKEv2 connectivity with various SKUs offering different throughput levels and capabilities. Google Cloud VPN supports both classic VPN and HAVPN, with HAVPN using IKEv2 and providing 99.99% availability through redundant tunnels. High availability in Cloud VPN requires multiple tunnels with redundant paths. Cloud providers typically recommend establishing tunnels to at least 2 VPN gateways in different availability zones. Dynamic routing using BGP allows automatic failover if one tunnel fails. Configure equal-cost multipath routing to use both tunnels simultaneously for higher aggregate throughput. Monitor tunnel health through metrics and alarms so you are notified if connectivity degrades. Some architectures use active-active tunnels for both availability and performance, while others use active-passive with one tunnel on standby. Transitive routing is often needed in cloud architectures where you have multiple VPCs or virtual networks that need to communicate through a central hub. Traditional spoke-to-spoke communication requires either full mesh IPsec tunnels, which doesn't scale well, or a transit architecture where a central VPN gateway routes between spokes. AWS Transit Gateway provides this capability, allowing multiple VPCs and VPN connections to communicate through a central hub. Azure Virtual WAN offers similar functionality. These services handle the complex routing and reduce the number of tunnels you need to manage. Performance optimization in Cloud vPages requires attention to several factors. Jumbo frames can improve throughput, but cloud networks may have MTU limitations, requiring careful configuration. Some cloud instances have enhanced networking capabilities with SRIOV, providing better performance. Monitoring metrics like tunnel throughput, packet loss, and latency helps identify performance issues. Cloud VPN services have throughput limits based on gateway SKU or instance size, so right-sizing your VPN capacity is important for meeting performance requirements. In very high throughput scenarios, Consider using multiple tunnels with load balancing or direct connections like AWS Direct Connect or Azure ExpressRoute instead of internet-based IPsec IKEv2 Security Best Practices. Implementing IKEv2 securely requires following established best practices that have been developed through years of deployment experience and security research. While IKEv2 is a well-designed protocol, misconfigurations or poor operational practices can undermine its security. Understanding and implementing these best practices ensures your VPN deployments provide the security properties they are intended to deliver. Algorithm selection is the foundation of secure IKEv2 deployment. Entirely avoid deprecated algorithms. Never use 3DES for encryption, SHA-1 for integrity, or DH groups smaller than group 14. These algorithms have known weaknesses that make them unsuitable for protecting sensitive data. Use AES-256 or AES-128 for encryption, with AES-256 preferred for high-security environments. For integrity, use SHA-256 or better when not using AEAD algorithms. For DH groups, use Group 14 as the minimum for traditional DH, or Group 19 for ECDH, choosing stronger groups for higher security requirements. Enable Perfect Forward Secrecy for all child SAs to ensure that the compromise of long-term keys does not expose past sessions. Authentication strength is critical for preventing unauthorized access. Certificate-based authentication is strongly preferred over pre-shared keys for scalability and security. Use 2048-bit RSA keys or 256-bit ECDSA keys as the minimum, with 3072-bit RSA or 384-bit ECDSA for higher security. Ensure certificates have appropriate validity periods. 1 to 3 years is common, balancing security against operational burden. Implement certificate revocation checking through CRLs or OCSP to ensure compromised certificates are detected. Never disable certificate validation or skip revocation checking in production environments, even if it simplifies testing. Key lifetime configuration affects security in subtle ways. Shorter lifetimes mean keys are refreshed more frequently, limiting the amount of data encrypted with each key and the time window for cryptanalysis. However, very short lifetimes increase rekeying overhead and can impact performance. Reasonable lifetimes are 1 to 8 hours for IKE SAs and 1 to 4 hours for child SAs. Traffic-based lifetimes should be set based on expected traffic volumes, with values like 100 megabytes to 1 gigabyte being common. Ensure soft lifetimes provide adequate time for rekeying to complete before hard lifetimes expire. Network security around VPN gateways requires careful attention. Implement firewall rules that allow only necessary ports. UDP 500 and 4500 for IKEv2, and IP Protocol 50 for ESP restrict source addresses where possible to known peer IP addresses. Deploy VPN gateways in DMZ networks isolated from internal resources, with additional firewalls controlling access from VPN users to internal systems. Implement IDS/IPS to monitor for attacks against VPN infrastructure. Log all VPN connection attempts, successful authentications, and failures for security monitoring and incident response. Operational security practices are as important as technical configurations. Implement monitoring for VPN health, tracking metrics like connection success rates, authentication failures, and tunnel availability. Alert on anomalies like sudden spikes in connection attempts that might indicate attacks. Conduct regular security assessments of VPN configurations, reviewing algorithm choices, certificate validity, and access controls. Maintain an inventory of all VPN endpoints and their certificates. Have a plan for emergency certificate revocation if keys are compromised. Keep VPN software and firmware updated to patch security vulnerabilities. Regular security audits and penetration testing help identify weaknesses before attackers do. Thank you for your attendance. Please consider subscribing to the channel.